जी बेटा अस्सलाम वालेकुम. So today we are solving paper 42 October November 2022. ठीक है जी. So the first question is calcium chloride is an ionic compound. The value of some energy changes are shown in table 1.1. Now first of all they're asking define lattice energy. So what is lattice energy? It is the energy change which occurs when 1 mole of an ionic solid formed from its gaseous ions. So energy change which occurs when 1 mole of an ionic solid formed from its gaseous ions. Now, the next question is use the data in table 1.1 to calculate the standard enthalpy change of formation of calcium chloride. It may be helpful to draw an energy cycle, show you working. Right, so now we have to calculate the standard enthalpy of formation from the data given in this table, table 1.1, right? So let's draw the energy cycle for calcium chloride. So starting with formation, calcium solid plus Cl2 gas, this gives CaCl2 solid. Now this is formation. Then next energy would be Ca calcium gas plus Cl2 gas, atomization of calcium. Then next energy change would be Ca2 plus gas plus Cl2 plus 2 electrons, ionization energy first and second. Then atomization of chlorine, so Ca2 plus 2Cl gas plus 2 electrons, atomization of chlorine multiplied by 2, and then chlorine will gain electrons, so electron affinity, so that would be an exothermic process, so energy will decrease. So Ca2 plus gas plus 2Cl minus gas, electron affinity, and finally the lattice enthalpy, right? So let's label the energy changes. So this was delta H, formation of CaCl2. This is delta H, atomization of calcium. Then delta H, ionization energy 1 plus 2 of Ca calcium. Then delta H, atomization of chlorine multiplied by 2, and delta H, electron affinity multiplied by 2, and delta H, lattice enthalpy. All right, so this is the energy cycle. Now let's find the formation. So delta H formation would be equal to so delta H formation of CaCl2, that would be equal to atomization of calcium, which is plus 193 plus electron affinity, sorry, ionization energy, first ionization energy 590, second 1150. So 590 plus 1150. Then atomization of chlorine, that would be atomization of chlorine is 121, so that would be multiplied by 2. So 121 multiplied by 2 plus electron affinity, which is minus 364 multiplied by 2, minus 364 multiplied by 2, and finally the lattice enthalpy, which is minus 2237. Let's find out the formation of calcium chloride. So that is equals to this is equals to 121 multiplied by 2 is equals to 242 plus minus 364 multiply by 2, that is equals to minus 728. All right, so 193 plus 590 plus 1150 plus 242 minus 728 minus 2273. 2237. So this is minus 790, right? So the final answer is minus 790 kilojoules per mole. All right, so next part is 3 possible values for the first electron affinity. 3 possible values for the first electron affinity of bromine are shown in table 1.2. One of them is correct. Place a tick by the correct value. Right, so they have given us 3 possible values for the first electron affinity of bromine. We have to find out which of them is the correct one. So we have electron affinity of chlorine, and we know this thing that the electron affinity of chlorine was minus 364, and as we move down in group 17, chlorine, bromine, iodine, astatine, so as we move down, the atomic radius increases plus shielding also increases. So when atomic radius will increase, the energy required to gain electron, it would get less negative. So it would be less negative, and that would be minus 342, right? So that would be minus 342. So this would be the correct answer. And the explanation, what would how would we explain this answer? That as bromine atomic radius is larger than Cl, therefore less energy releases. All right, now the next part is the enthalpy change of hydration of the chloride ion can be calculated. The enthalpy change of hydration of chloride ion can be calculated using the lattice energy of calcium chloride and the data shown in table 1.3. So they've given us the standard enthalpy change of solution of calcium chloride and standard enthalpy change of hydration of calcium ion. Define the following term. Standard enthalpy of solution, it is the energy change which occurs when 1 mole of an ionic solid dissolves in water. Energy change which occurs when mole of ionic solid dissolves in water, right? And enthalpy of hydration, it is the energy change which occurs when 1 mole of gaseous ion dissolves in water. Right, so 1 mole of gaseous ion dissolves in water, that is standard enthalpy of hydration. Now, calculate the standard enthalpy change of hydration. Calculate the standard enthalpy change of hydration of the chloride ion. It may helpful to draw an energy cycle, show all your working. So we have to calculate the standard enthalpy change of hydration of chloride ion. The values that they have given us is the hydration of calcium ion, right? Solution of calcium chloride and lattice enthalpy. So first we will draw the energy cycle. So Ca calcium Ca2 plus gaseous ions, Ca2 plus gaseous plus 2Cl minus chloride ion gaseous, this gives CaCl2 solid. This is delta H lattice enthalpy, and then Ca2 plus Aq plus 2Cl minus Aq hydration. And so here we have hydration of delta H So here we have hydration of Ca2 plus and hydration of Cl minus multiply by 2, and this is solution of CaCl2. From this cycle, we can say that delta H hydration is equal to lattice plus delta H solution. So delta H hydration of calcium ion, which is hydration of calcium ion is minus 1650. So minus 1650 plus hydration of chloride ion, that we have to find out. So it is 2x is equals to lattice enthalpy of calcium chloride. This is given here. So this is lattice enthalpy of calcium chloride minus 2237 minus 2237 plus solution of calcium chloride, which is minus 83. So plus minus 83. So let's find out the hydration of chloride ion. So that would be equals to 2x would be equal to 2237 plus 83 minus 1650 670 minus 670, and x would be equal to 670 minus 670 divided by 2. So divide by 2, that is 335, negative 335 kilojoules per mole. So this is the hydration of chloride ion, right? And if you have any confusion, I can write the values here. So this is delta H, this is hydration of Ca2 plus, this is hydration of chlorine, and this is lattice enthalpy, and this is solution enthalpy. All right, now the next part of the question says calcium fluoride can be synthesized directly from its elements. Calcium fluoride can be synthesized directly from its elements. The value for its formation is minus 1214 kilojoules per mole. Predict the sign of the entropy change for the synthesis. Explain your answer. So they're saying that it can directly be synthesized from its elements. So if we write the formation equation for calcium fluoride, that would be calcium solid plus fluorine gas. This gives us calcium fluoride solid. So we have to predict the value of entropy change. So the entropy change would be negative. It would be negative, and the reason is on the reactant side we can see that there is 1 mole of gas, but on the product side we have only solid. So the moles of gas are decreasing, and whenever in a chemical reaction number of moles of gas are decreasing, that means disorder is also decreasing. So the sign of entropy change would be negative, and the reason is the moles of gas are decreasing during the reaction. All right, now the last part of this question is use the value of delta H formation of calcium fluoride given in E and your answer in E1, right? To predict how the feasibility for this synthesis will change with increasing temperature. To predict how the feasibility for this synthesis will change with increasing temperature. If we increase the temperature, will it become more feasible that calcium fluoride will form, or it gets less feasible? So we can see that delta H for the reaction is, delta H for this reaction is negative. That means reaction is exothermic and disorder is increasing, which is also negative, right? Now the equation that we would use is delta G is equals to delta H minus T delta S, and delta H in this equation is negative. Formation, the value of formation that they have given us, so it is negative, and minus T and delta S. Entropy disorder is also decreasing, so this is also negative. So minus minus, it becomes positive, so the factor T delta S is positive in this case. And if we increase the temperature, that means this factor would also increase, and at higher temperature it can become greater than T delta S can become greater than delta H. So at higher temperature, the feasibility, once this factor, once this T delta S becomes greater than delta H, the value of delta G will become positive, and that means reaction will become less feasible. So as the temperature increases, at higher temperature, T delta S will become more positive. At higher temperature, T delta S will become more positive, and the value of delta G becomes positive as well. Therefore, reaction will be less feasible at higher temperature. All right, so this is question number 1. All right, now the next question is nitrogen mono. This question is related to rate of reaction, chemical kinetics. And it says that nitrogen monoxide reacts with ozone. All right, nitrogen monoxide is reacting with ozone. This reaction is first order with respect to both nitrogen monoxide and ozone. At 298 Kelvin, the rate constant K is 11,500 moles per dm cube, mole inverse dm cube per second. Complete the rate equation for this reaction, right? So first of all, we have to write the rate equation. They have given us the order that with respect to both the reactants, with respect to nitrogen monoxide and with respect to ozone, it is first order reaction. So rate would be equal to rate constant K, concentration of nitrogen monoxide, concentration of ozone. So this is the rate equation for this reaction. A reaction is carried out in which the initial concentration of nitrogen monoxide and ozone are both 1.20 into 10 raised to power minus 6 moles per dm cube. Calculate the initial rate of this reaction, state its unit. Right, so we have to calculate the initial rate of the reaction. So that would be equal to, the initial rate would be equal to, the value of K is 11,500 multiply by initial concentration is 1.20 into 10 raised to power minus 6 multiply by 1.20 into 10 raised to power minus 6, because both of the reactants have same concentration. So the answer would be 11,500 multiply by 1.20 multiply by 1.20. So that is equals to 16560 multiply by 10 power minus 12, and if we write it in standard form, then it would be 1.66 into 10 raised to power 1, 2, 3, 4. So that would be 10 raised to power minus 8. So 1.66 into 10 raised to power minus 8. So this would be the rate of the reaction. And now the units. So the unit would be rate constant. They have given us the unit of rate constant, which is mole inverse dm cube second inverse, and the unit of concentration is mole per dm cube. So that would be equal to mole square dm minus 6, because this is moles per dm cube and this is moles per dm cube. So mole square would be cancelled with mole inverse. So we are left with mole in the numerator, and dm cube is cancelled with dm minus 6. So we are left with dm cube in the denominator. So the unit would be mole per dm cube per second. So this is the unit of rate of reaction. All right. Now the next part is the reaction described in A2 is monitored over a period of time. Predict whether or not the graph of nitrogen monoxide, against time, concentration of nitrogen monoxide against time under these conditions shows that the reaction has a constant half-life. Explain your answer. Right, so they're saying that the reaction described in A2 is monitored over a period of time. This reaction, in which the concentrations are same for both the reactants, and under these conditions show that the reaction has a constant half-life. Explain your answer. So because the reaction is first order with respect to both the reactants, now you have to just understand this thing, that the reaction is first order with respect to the concentration of nitrogen monoxide, and it is first order with respect to concentration of ozone. So that means overall order of the reaction is 1 plus 1, that is second order reaction, right? So it is a second order reaction. If we write the overall order, it is a second order reaction. Now, as the question says that predict whether or not the graph of the concentration of nitrogen monoxide against time. Let's suppose if we plot a graph of concentration of nitrogen monoxide against time. So for a first order reaction, half-life remains constant. But because we are doing the reaction with same concentration of nitrogen monoxide and same concentration of ozone, which is this 1.20 into 10 raised to power minus 6. So rate would be affected by the concentration of nitrogen monoxide, and it would also be affected by the concentration of ozone. So overall, it is now a second order reaction, right? If you want to observe the effect of concentration of nitrogen monoxide, then you have to take the other reactant in large amount. But because we are doing the reaction with same concentration of both the reactants, that means this would not be a constant half-life. So this would not be a constant half-life, not constant half-life. And the reason is because reaction is second order, right? So reaction is second order, so we'll not get a constant half-life. Nitrous oxide decomposes into its elements. Nitrous oxide decomposes into nitrogen and oxygen at a high temperature. A small amount of platinum wire is added to a large amount of nitrous oxide. A small amount of platinum wire is added to a large amount of nitrous oxide. The reaction follows zero order kinetics. The platinum wire behaves as a catalyst. Right, so the reaction follows zero order catalyst. That means the concentration of nitrous oxide does not affect the rate of reaction. Sketch a graph on the axis below of the reaction rate against time for the catalyzed decomposition of nitrous oxide under these conditions. Right, so as they have told us that the reaction is zero order with respect to the concentration of nitrous oxide, that means with respect to time, the reaction rate will remain constant. So because reaction is zero order, that means the rate of reaction will remain constant. It will remain constant. It would not be affected by the concentration of nitrous oxide. Now, the next question is sketch a graph on the axis below. Sketch a graph on the axis below of concentration of nitrous oxide against time for this reaction. Right, so the concentration of nitrous oxide does not affect the rate of reaction. It does not affect the rate of reaction. That means it will decrease at a constant rate. Right, rate will remain constant as the gradient of concentration time graph gives the rate of reaction. So the gradient of this graph would remain constant. That means we'll get a negative slope. So it would be something like this. Right, so it would be a straight line with a negative slope. So concentration rate remains constant. Now, the next part of this question is platinum behaves as a heterogeneous catalyst in this reaction. Describe the mode of action of a heterogeneous catalyst. So, heterogeneous catalyst, how it acts. Initially, the reactants get adsorbed onto the surface of catalyst. right? So you can say that adsorption of N2O onto the surface of catalyst, right? Let's suppose if this is the catalyst, so N2O molecules, they get adsorbed to the surface of the catalyst. Next, the bonds the bonds within the nitrous oxide get weakens once it get adsorbed onto the surface of the catalyst. So the bonds within N2O weakens, it gets elongated. Let's suppose if this is a nitrous oxide molecule. So once it get adsorbed onto the surface of the catalyst, the bond within the molecule, these are starts getting weakened, right? And it starts converting into the product. So the final state would be, first stage is adsorption, and due to that adsorption, the bonds within the molecule, they starts getting weak. And the last stage is the desorption phase. Once product forms, the bonds of the product molecules, they are much stronger than the bonds they have made with the catalyst. So they break the connection with the catalyst, which we called desorption. So once products form, desorption occurs, and the products leave the surface of catalyst. All right, so these are the three stages in which heterogeneous catalysts work. Now, the last part of the question is that suggest a reason why this reaction has zero order kinetics when the amount of nitrous oxide is large and the amount of platinum is small. Now, this is very tricky question. They're saying that, let's suppose if this is the surface of catalyst, let's suppose this is the surface of catalyst. Now we have very small amount of platinum present, and we have N2O in large amount. So if we have N2O in large amount, then its concentration does not matter. If we have N2O in large amount, then its concentration does not matter if the amount of platinum is small. The reason is, if we have a large concentration, now this is a large concentration of N2O and small amount of platinum. So because we have very small amount of platinum, so very few N2O can be attached to this small amount. Very few N2O can be attached. So the concentration of N2O doesn't matter here, right? It doesn't affect the rate of reaction. If you take a large amount of N2O or if you take a small amount of N2O, very few numbers can be attached to platinum. Therefore, the concentration of nitrogen monoxide, the concentration of nitrous oxide, let's suppose if I take 10 molecules, if only 2 molecules can be attached here, let's suppose if only 2 molecules of N2O can be attached, then it doesn't matter if I take 10 molecules of N2O or 1000 molecules or 100 molecules, because the reaction only occurs on the surface of platinum and we have very small amount of platinum. All right, so the active sites of the catalyst would always be occupied, and it doesn't matter if you have large concentration of N2O present in the reaction chamber. So the reason is that due to the small amount of platinum, all the active sites where adsorption occurs, all the active sites will remain occupied. So if you have N2O present in large amount, it would not affect the rate of reaction, right? Because the reaction only occurs on the surface of catalyst and it is already occupied. So once desorption occurs, then other reactant particles will get attached to the surface, and that is why its concentration will not affect the rate of reaction. All right, so this is the end of the question 2. All right, so this is question number 3, and it says that data should be selected from table 3.1 in order to answer some parts of this question. So they've given this E naught values, and the first part of the question is an electrochemical cell can be constructed from magnesium ion half cell and manganate ion Mn2 plus half cell. The standard cell potential of this cell can be calculated. The standard cell potential of this cell can be calculated using the standard electrode potentials of two half cells. Define standard electrode potential. Include details of the standard conditions used. Right. So the standard electrode potential is, it is the potential, or it is the voltage. It is the potential measured, it is the potential produced by a half cell when in contact with a standard hydrogen electrode. So this is the definition of standard electrode potential under standard conditions. And what are the standard conditions? Temperature 298 Kelvin, pressure 1 atm, and concentration 1 mole per dm3. So these are the standard conditions, right? So this is the definition of standard electrode potential. Now, next part is complete the diagram below to show an electrochemical cell constructed from magnesium ion magnesium half cell and manganate ion Mn2 plus half cell. Label your diagram. So we have a metal in contact with metal ions, and we have two ions of a metal, manganate ion and manganese 2 plus ion, in contact with each other, right? So let's suppose we have a magnesium wire in one electrode, or magnesium rod. Let's suppose if this is magnesium in contact with Mg2 plus, right? So let's suppose this is magnesium in contact with 1 molar, or capital M, because capital M represents the concentration in mole per dm cube, 1 molar Mg2 plus, right? And this is magnesium, and it is in contact with, in the other half cell we have, because the other half cell contains these two ions, so this would be 1 molar MnO4 manganate ion and 1 molar Mn2 plus ion. So the solution contains both the manganate ions and Mn2 plus, and to conduct the electricity we would have a platinum wire placed in this electrode. So this is a platinum wire, and both this platinum wire and magnesium rod, they are in contact with each other through a voltmeter, right? So they are in contact with each other. So magnesium wire, platinum wire, and now we have this voltmeter, and both these half cells, they are connected to each other through a salt bridge. The half cells, they are in contact with each other through a salt bridge, right? So this is the complete diagram for this half cell. Now the next part is use a positive sign and a negative sign to identify the polarity of each of the two electrodes in your diagram. Use an arrow and the symbol E to show the direction of electron flow in the external circuit. Now this half cell, this is magnesium in contact with Mg2 plus, and this the standard electrode potential is minus 2.38. So its standard electrode potential is minus 2.38 volt. And this half cell, it is the half cell in which MnO4 manganate ions are in contact with Mn2 plus, and its electrode potential is Here we have manganate ion in contact with Mn2 plus. So its electrode potential is plus 1.52. So its electrode potential is plus 1.52, and its electrode potential, because it is positive, and the other electrode potential, it has a negative value. So that means this would this would gain electron. Here we would have reduction. Just remember this thing, that if we have a higher value, or if we have a positive value for standard electrode potential, that means at that particular electrode reduction would occur, gain of electron occurs. And where we have a negative value, here oxidation occurs, loss of electron. So because at this particular half cell, magnesium in contact with magnesium ion, oxidation is happening, and where oxidation occurs, it is anode, and anode is represented by negative sign because it is losing electron. So they ask us in the question that use a positive and negative sign to identify the polarity of each of the two electrodes. So the magnesium electrode, it would be negative, and where gain of electron occurs, that means where reduction occurs, this is cathode. And in these kind of cell diagrams, cathode is represented by positive. Its polarity is positive because electrons are attracting towards it. So this is positive electrode, and this is negative electrode. And the last part is use an arrow and the symbol E to show the direction of electron flow in the external circuit. So the electrons are traveling from magnesium half cell towards manganate half cell. So this is the direction of electron flow. Now, the next part is calculate the standard cell potential of this cell. So the standard cell potential is the formula which we use to calculate standard cell potential is E reduction minus E oxidation. And E reduction would be the value which is more positive. So this is the reduction potential plus 1.52, and this is oxidation potential minus 2.38. So plus 1.52 minus 2.38. So the standard cell potential would be 1.52 plus 2.38, which would be equal to 3.9 or 3.90, because though both the values are up to 2 decimal places, so the final answer would also be up to 2 decimal places, 3.90. Construct an equation for the cell reaction. Right, so we have to write the equation for the cell reaction. So this is the half reaction which shows the oxidation, and this is the half reaction which shows the reduction. So if we combine these two reactions, now because in magnesium half cell oxidation is happening, that means this reaction will occur backward. So this is the reactant side, this is the product side. So if we write the equations, Mg losing electrons becomes Mg2 plus, and the other reaction would be happening in forward direction, gain of electrons. So that would be MnO4 minus plus 8H plus 5 electrons gives Mn2 plus 4H2O. Now to balance the electrons, because we have to cancel out the electrons in the final redox reaction, we do not write electrons. This equation would be multiplied by 5, and this equation would be multiplied by 2, so that we have 10 electrons in both the equations. So it would be 5Mg2 plus, and this would become 10 electrons. This would be 2MnO4, 16H plus, 10 electrons, 2 and 8H2O. Right, so 10 electrons would be cancelled out by 10 electrons, and now we are left with 5Mg plus 2MnO4 minus 5Mg plus 2MnO4 minus plus 16H plus. We are combining both the reactant sides, 16H plus, and on the product side we have 5Mg2 plus 2Mn2 plus 5Mg2 plus 2Mn2 plus 4H2O. So this is the final equation. So this is 8H2O, right? 8H2O. All right. So this is the final equation. You just have to add up both the half equations and the electrons must be cancelled out. Now the next part of the question is predict how the cell reaction will change if at all. So they're talking about the feasibility of the reaction when the solution in the Mg2 plus Mg plus Mg half cell is diluted by the addition of a large volume of water. So they're talking about this half cell, that if we add a large amount of water into it, so definitely the concentration will change when we add a large amount of water into it. So the half equation is Mg2 plus 2 electrons. This is reversible reaction Mg, right? And the reaction is happening in this direction. Now they're saying initially it was happening at concentration 1 mole per dm cube. Now they're saying if we increase the concentration, or if we increase the amount of water into it, or if large amount of water is added, so increase the amount of water. So if we add a large amount of water, definitely solution gets diluted. Solution gets diluted, that means the concentration of the solution decreases. If we add more water, the concentration of Mg2 plus ions will decrease, and if the concentration of Mg2 plus ion decrease, that means this equilibrium will shift backward. That means more oxidation occurs, more oxidation would occur, and if more oxidation occurs, that means this value, which is the value of the E naught value, was minus 2.38, and if more oxidation occurs, that means this value would get more negative, right? This value would get more negative, and if the value of this particular half cell gets more negative, that means reaction will become more feasible. So which implies that the cell reaction will not change. So there would be no effect on the feasibility of the reaction. Reaction will occur in the same direction. From this particular half cell, electrons would be lost, and at this particular half cell, electrons would be gained. So there will be no change in the feasibility of reaction. So we can write down the answer. This was just for the explanation. Now how you'll write down the answer, that there will be no change in the feasibility of reaction. No change in the feasibility of reaction as amount of water increases, the solution gets diluted, and equilibrium shifts on the Mg2 plus side. That means the E reduction potential, E naught, gets more negative. Electrode potential gets more negative. So if it gets more negative, that means the overall answer, if this value, we are talking about this value gets more negative, that means the overall answer would become more positive, and there will be no change on the feasibility of the reaction. Reaction would occur. Now the next question is, the molten magnesium salt is electrolyzed. Molten magnesium salt is electrolyzed for 15 minutes by a constant current. 4.75 into 10 raised to power 22 magnesium atoms are produced at the cathode. Calculate the value of the current used. A molten magnesium salt is electrolyzed. Let's suppose this is electrolytic cell where we have electrodes, and this is battery. So we are electrolyzing it, and we have a molten magnesium salt. That means we have Mg2 plus ions present in the solution, which would be moving towards cathode, right? So the time for which this electrolysis occurs is 15 minutes. And how many atoms are produced at the cathode? 4.75 into 10 raised to power 22 atoms. First, let's just write the equation which would be happening at the cathode. So Mg2 plus ions would be gaining 2 electrons, and it becomes Mg. So first, let's calculate the moles of magnesium, right? We have atoms of magnesium. Let's calculate the moles of magnesium. So moles of magnesium, that would be equal to 4.75 into 10 raised to power 22 divided by Avogadro's number, which is 6.02 into 10 raised to power 23. So the moles of magnesium is 0.78 into 10 raised to power minus 1, or 7.8 into 10 raised to power minus 2. Right, so these are moles of magnesium. Next, if we convert it into moles of electrons, so the molar ratio between magnesium and electron is 1 to 2. So if we want to convert moles of magnesium into moles of electron, we would multiply it by 2. So 7.8 point, so this would be equal to 0.156. These are moles of electrons. And next we will convert it into charge. So we know this thing that 1 mole of electron carries 96,500 coulombs, and 0.156 moles of electron would carry what amount of charge? So that would be equal to 0.156 multiplied by 96,500, and that is 15054 coulomb. So this is the amount of charge carried by 0.156 moles of electrons. And now we have to find out the current. So we know this thing that charge is equals to current into time, and the charge carried by electrons is 15054 is equals to current we have to find out, multiplied by time is in 15 minutes, multiply by 60 to convert it into seconds. So the final answer would be 15 into 60, that is equals to 900, and 15054 divided by 900. So the final answer is 16.72 ampere. So the current used is 16.72 ampere. Okay, so now question number 4, and it says that the value of the solubility product of iron 3 hydroxide is given by the following expression. They have given us the expression of KSP and the value of KSP. Calculate the solubility of FeOH3 in water. Okay, so we have to calculate the solubility of FeOH3 in water, and if we make an equation for this if we make an equation for the solubility of FeOH3, so that would be FeOH3 partially dissolved to give Fe plus 3 ion plus 3 moles of hydroxide ions. Okay, and we have to calculate the solubility of iron 3 hydroxide. Let's suppose if this is X, so it gives us X moles of Fe plus 3 ions and 3X moles of hydroxide ions. So the expression of KSP is equals to concentration of Fe3 plus into concentration of OH minus Q. So KSP is 2 into 10 raised to power minus 39, which is equals to concentration of X, which is X, concentration of Fe plus 3, which is X, and hydroxide, which is 3X. So this would be X into 3X cube, and 2 into 10 raised to power minus 39 would be equal to 4X power 4. So X power 4 is equals to 2 into 10 raised to power minus 39 divided by, this is the cube of 3 is 27, so this would be upon 27. And to find out the value of X, we would have to take the fourth root of this value, so that would be equal to 2 into 10 raised to power minus 39 divided by 27, and the fourth root of this value is 9.28 into 10 raised to power minus 11. So this is the solubility of iron 3 hydroxide. Now the next part is calculate the solubility of iron 3 hydroxide in 0.01 mole per dm cube barium hydroxide. Right, so instead of dissolving it in water, if we dissolve it in barium hydroxide, and its concentration is 0.01 moles per dm cube, right? So now barium hydroxide, we know this thing, the solubility of group 2 hydroxides increases down the group. So barium 2 hydroxide is soluble in water, right? So that means the concentration. Now, if we write the expression of KSP for iron 3 hydroxide, so that is, so the expression of KSP is KSP is equals to concentration of Fe3 plus and concentration of hydroxide ions. But now the concentration of hydroxide ion, it will depend on barium hydroxide because this is more soluble than iron 3 hydroxide. And if we write the equation for the solubility of barium hydroxide, it is BaOH2. When it dissolves, it would be completely dissolved in water. So this gives us Ba2 plus 2 moles of hydroxide ion. So the concentration of barium hydroxide in water is 0.01. That means the concentration of hydroxide ion in water would be 0.02 because the ratio is of 1 to 2. So we get 0.02 moles of hydroxide ions, right? So now the solubility of iron 3 hydroxide, the expression would become KSP is 2 into 10 raised to power minus 39 is equals to the concentration of iron plus 3 ion is X into concentration of hydroxide ion would depend on barium hydroxide, which would be 0.02 because the hydroxide ions are now mainly coming from barium hydroxide cube. So the final answer would be this would be X is equals to 2 into 10 raised to power minus 39 and the cube of 0.02 is 8 into 10 raised to power minus 6. So the final answer would be 0.25 into 10 raised to power minus 33, and this would be 2.5 into 10 raised to power minus 34. So this would be the solubility of iron 3 hydroxide in 0.01 moles of barium hydroxide. All right, now the next part is FeOH3 is less soluble in, as you can see that the solubility of FeOH3 in water is 9.28 into 10 raised to power minus 11, and its solubility in in barium hydroxide is 2.5 into 10 raised to power minus 34. So that means it is less soluble in barium hydroxide. So the solubility of iron 3 hydroxide is less soluble in barium hydroxide than it is in pure water. So name this effect. This is known as common ion effect. The presence of hydroxide ion, it decreases the solubility by shifting the equilibrium on the undissolved side. So this is known as common ion effect. Now the next part is the numerical value of Ka of HBRO, which is some weak acid, is 2 into 10 raised to power minus 9. X is a solution of HBRO which contain 4 into 10 raised to power minus 3 moles of HBRO in 100 cm cube of solution. In this solution, the following equilibrium is established in which there are two conjugate acid-base pairs. Right, so HBRO dissolves in water, we get BRO minus plus H3O plus. Define conjugate acid-base pair. So what is a conjugate acid-base pair? Once an acid loses a proton, let's suppose HCl, once it loses proton, it becomes Cl minus, and this HCl and Cl minus is a conjugate acid-base pair. Right, so the particles or the species which differ by H plus ion, they are conjugate acid base pair. For example, once ammonia gains H plus ion, it becomes NH4 plus, and ammonia and NH4 plus are conjugate acid base pair. So what are conjugate acid base pairs? They are particles that differ by H plus ion. Identify the two conjugate acid base pairs shown in the equation above, right? So the first conjugate acid base pair is HBRO is losing proton. Once it loses proton, it becomes a BRO minus. So that means the first conjugate acid base pair is HBRO and BRO minus. if HbRO is an acid, BrO minus is a conjugate base. And the other one is H2O is gaining proton, right? So that means it is acting as a base. And once it gains proton, it converts into H3O plus. So that means H2O is a base and H3O plus is the acid, right? So these are the conjugate acid base pairs. Next part of the question is calculate the pH of solution X, show all your working. So because HbRO is a weak acid, and for weak acid, first we have to find out the concentration of H ions, which can be calculated by this formula. The concentration of hydrogen ion would be equals to square root of Ka into concentration of weak acid, right? So the value of Ka is given in the question, which is 2 into 10 raised to power minus 9. 2 into 10 raised to power minus 9. And the concentration of weak acid, for concentration of weak acid, they are given as the moles and the volume of solution. So the concentration would be equals to number of moles upon volume, which is 4 into 10 raised to power minus 3 divided by 100 divided by 1000, right? So this is the volume of solution in dm cube. So the final answer would be 4 into 10 raised to power minus 2. So this is the concentration of solution of weak acid. So 4 into 10 raised to power minus 2. So the concentration of H ions would be 8 into 10 raised to power minus 11, which would be equal to 8.94 into 10 raised to power minus 6. And the pH would be equals to negative log of concentration of H plus ion, which is 8.94 into 10 raised to power minus 6. So this would be negative log 8.94 into 10 power minus 5.05. So the pH is 5.05. Now the last part of the solution is a solution containing now the last part of the question is a solution containing 2 into 10 raised to power minus 3 moles of NaOH is added to solution X. A buffer solution is formed. Calculate the pH of this buffer solution, right? So finally we have to calculate the pH of the buffer solution, which now we have added sodium hydroxide in the solution of weak acid, which is HbRO, reacts with NaOH, so neutralization occurs, we get salt NaBrO plus H2O. Now this mixture of this salt and weak acid will act as a buffer. The moles of weak acid we have is 4 into 10 power minus 3, and the moles of sodium hydroxide is 2 into 10 power minus 2. So that means NaOH is the limiting reagent. So the salt we get would also be 2 into 10 raised to power minus 2. And this strong base would be completely utilized. And the amount of weak acid which we are left would be equals to 2 into 10 raised to power minus 2. Right. So this is the moles of salt, and these are the moles of minus 3. And this is also minus 3. Now, so these are the moles of weak acid and salt, right? And if we want to convert it into concentration, so because we have 100 cm cube, so the concentration would be 2 into 10 raised to power minus 2, and this its concentration would also be 2 into 10 raised to power minus 2. Now to calculate the pH of this buffer, first we would have to calculate the concentration of H ion, and now the formula of acid dissociation constant would be HA. For buffer we use this formula, concentration of H ion into concentration of salt upon concentration of acid. And because concentration of salt and acid are equal, so this can be easily cancelled out, and that means the concentration of H plus ion is equals to Ka, which is 2 into 10 raised to power minus 9. So now if you want to calculate the pH, so pH would be equal to negative log concentration of H ion, which is 2 into 10 raised to power minus 9. and the final answer would be 8.70. So this is the pH of buffer solution. Okay, so now the next question, question number 5, relates to transition elements. Copper is a transition element and it forms a wide variety of compounds. Define transition elements. What are transition elements? These are elements which form one or more stable ions with partially filled d-suction. All right. Now, an aqueous solution of copper 2 sulfate contains an aqueous solution of copper 2 sulfate contains hexaaqua copper 2 plus ion complex ions, and if an excess of concentrated hydrochloric acid is added to this solution, a ligand exchange reaction occurs and CuCl4 2 minus complex ions are formed. Complete table 5.1 to state the geometry, the coordination number of copper, and one bond angle in each of the two complex ions. Right, so the geometry of hexaaqua copper 2 plus ion would be octahedral because 6 ligands are attached, so this would be octahedral, and its coordination number is, because 6 water molecules are attached and water molecule is a monodentate ligand, so coordination number is 6, and the bond angle would be 90, right? Between water molecules, the bond angle would be 90 degree. In case of CuCl4 2 minus, because coordination number is 4, Cl is again monodentate ligand. So when all the 4 ligands are halogens, then geometry is tetrahedral and bond angle would be 109.5 or 109 degrees. In an isolated copper 2 plus ion, the d orbitals are all degenerate. The 5 d orbitals are degenerate and degenerate. In a complex ion such as hexaaqua copper 2 plus ion, the d orbitals are non-degenerate. Define degenerate and non-degenerate in this context. So degenerate orbitals are when all the 5 orbitals are at the same energy level. All the 5 d orbitals are at same energy level. Okay, if all the 5 d orbitals are at the same energy level, that means they are degenerate, and non-degenerate when they are not at same energy level. Next, explain why the solution of the two complex ions. Solution of the two complex ions are of different colors, and the color is due to the energy absorbed by the transition metals from the visible range. So because this is only 1 mark question, so we can say that the solution of the two complex ions, they're talking about these two solutions, why they have different colors, although transition metal is same, but because different ligands are attached, so that's why they would absorb different amount of wavelength, right? So different wavelength will be absorbed as ligands and geometry is different. Copper 2 plus forms a complex ion containing water molecules and ethane dioate as ligands. The formula of the complex is this. The ethane dioate is a bidentate ligand. Explain what is bidentate ligand. A ligand which can form 2 dative bonds with the central metal ion. A ligand which can form 2 dative bonds with the central metal ion is bidentate ligand. There are 3 stereoisomers with this formula. complete the three-dimensional diagrams to show these three stereoisomers, right? So now we have to draw three stereoisomers. Because the geometry is octahedral, copper has two water molecules, H2O, and two ethane diovate ions, right? So two ethane diovate ion, and we have to draw the three-dimensional structure, right? So three-dimensional structure would be something like this. Right, so this would show both cis-trans isomerism and optical isomerism. So let's just first draw the cis-trans isomers. So cis-trans isomers would be, in cis isomers, the like ligands, which are water molecules, they would be at an angle of 90 degrees. Right, so let's suppose this is water molecule, this is water molecule, and ethane dioate, C2O4. Right, so C2O4 is carbon-carbon double bond. Now this is ethane dioate, right? And we can just simply draw ethane dioate as, I'm going to draw it like this. And this is one ethane dioate and the other one is this. These are two ethane dioate molecules, and in this structure the water molecules are 90 degrees apart. So this is cis isomer, and if we draw them at an angle of 180 degrees, then it becomes a trans isomer. So in trans isomer, the water molecules would be at 180 degrees apart, and both the ethane dioate ions would be drawn like this. So this is a trans isomer, and now the third isomer would be the optical isomer, and both the optical isomer. And because this cis isomer has no plane of symmetry, right? So cis isomer would have optical isomer, would have its optical isomer, right? So its optical isomer would be drawn, it would be a non-superimposable mirror image, and we'll draw it like this. H2O and right, so this is another cis isomer. Let's suppose if this cis isomer rotates the light in clockwise direction, this will rotate the light in anti-clockwise direction. So these are three stereoisomers. Now the next part is use your answer to C2 to answer this question. Stereoisomers 1, 2, and 3 shows two different types of isomerism. Name these two types of isomerism. And for each type of isomerism, identify the pair of stereoisomers that demonstrate this isomerism. So the first type of isomerism is geometrical. Geometric isomerism, and which is shown by stereoisomer 1 and 2. This is trans isomer where the angles are different. So isomer 1 and 2 are geometric isomers, and the other type of isomerism is optical isomerism. And structure 1 and 3 shows optical isomerism, 1 and 3. All right, now the next part of the question is, a solution contain 3.70 grams of this complex, dissolve in 100 cm cube of solution. A 25 cm cube sample of this solution is warm and then oxidized by 0.01 mole per dm cube acidified potassium manganate. The equation for the redox reaction is potassium manganate will react with ethane dioate ions and a redox reaction will occur. Calculate the minimum volume of 0.01 mole per dm cube acidified potassium manganate needed to oxidize all the ethane dioate ions in the 25 cm cube of sample. Show all your working. Right, and the MR of this complex is 321.5. So we have to calculate the minimum volume of the oxidizing agent which is needed to oxidize the ethane dioate ions. And for that they have given us the mass of this complex, right, and the volume of solution and concentration of dilute potassium manganate. So first of all, we will calculate the moles of moles of the complex, right? So moles of the complex would be equal to mass, which is 3.70, divided by mr, which is 321.5. So 3.70 divided by 321.5, this is equals to 0.0115. 0.0115. Now these are moles of the complex, and if we want to convert it into moles of the ethane diovate ion, so you can just simply look at the formula of this complex, that 1 mole of this complex contains 2 moles of ethane diovate, right? It contains 2 moles of ethane diovate. So this, you can see, is 2, right? So 1 mole of this complex contains 2 moles of ethane diovate. So that means if I just simply multiply the moles of complex with 2, we get moles of ethane diovate. Multiply by 2, and this is moles of ethane diovate, which is 0.0230. 0.0230. Now these are the moles of ethane diovate in 100 centimeter cube. In 100 centimeter cube. But the redox reaction which has been occurred, for that redox reaction we have taken 25 cm cube sample, right? So these are the moles in 100 cm cube. So what would be the number of moles in 25 cm cube? So we just have to simply divide it by 4. So that would be equals to 0.0230 divided by 4, and that would be 5.75 into 10 raised to power minus 3. So moles of C2O4 2 minus in 25 cm cube would be 1/4 of the moles in 100 cm cube, and that is 5.75 into 10 power minus 3. Next, because we have to find out the volume of MnO4, we'll convert the moles of ethane diovate into moles of MnO4 by using this ratio, 5:2, right? So the moles of ethane diovate and the moles of MnO4, they have this ratio C2O4 ethane diovate and MnO4 minus. They are reacting with each other in a ratio of 5:2. So if we have 5.75 into 10 power minus 3 moles of ethane diovate, then the number of moles of manganate ion would be 2.3 into 10 raised to power minus 3. 2.3 into 10 raised to power minus 3. And finally, we have to calculate the volume. So which would be equal to C is equals to N upon V, or V is equals to number of moles, which is 2.3 into 10 raised to power minus 3 divided by concentration, which is 0.01. So divided by 0.01. So this would be equal to 0.23 dm cube. And because they've asked they have asked the answer in centimeter cube, so multiply it by 1000, so that would be equal to 230 centimeter cube. So this is the minimum volume of KMnO4 for this required for this redox reaction. Now the last part of the question is copper 2 nitrate and barium nitrate both decompose when heated. Copper 2 nitrate decomposes at a lower temperature than barium nitrate. Suggest a reason for this difference. Explain your answer. Right, so the thermal decomposition, it depends on the ion polarization, and both copper nitrate CuNO3 2 and barium nitrate BaNO3 2. Now both copper 2 nitrate and barium nitrate, they have same anions, right? And the charge of the cation is also same, which is +2 and +2. So that means the polarization of the anion, it only depends on, in this case, it only depends on cationic radius. And because it says that the copper 2 nitrate decomposes at lower temperature than barium nitrate, and we know this thing that as cationic radius increases, the ion polarization decreases, and it becomes more thermally stable. So we can say that they've asked us to suggest a reason for this difference. Why copper 2 nitrate decomposes at a lower temperature than barium nitrate? So we can just simply say that copper ion is smaller than barium ion, due to which more ion polarization occurs in copper 2 nitrate. Therefore, more covalent character, right? And that's why it decomposes at a lower temperature, because as the covalent character increases, the thermal decomposition becomes more easier, because it becomes easier to distort the nitrate ion, and it easily breaks into nitrogen and metal oxide. All right, so now the next question is question number 6. An aqueous solution of cobalt 2 chloride is pink color due to the presence of hexa aqua cobalt ions. Complete table 6.1 to describe what is observed when the named reagent is added to an aqueous solution of cobalt 2 chloride. So when NaOH is added, an acid-base reaction would occur, and we get cobalt 2 hydroxide, which would give precipitate. So that means state of the cobalt containing product would be solid, and the color of this cobalt 2 hydroxide would be of blue color, right? And then when we add an excess of concentrated hydrochloric acid, then ligand substitution reaction occurs, and all of the 6 water molecules would be replaced by 4 chloride ligands, right? So the state of the cobalt containing product would be aqueous, and the color of the cobalt containing product, which would be COCl4 2 minus, this would give blue colored solution. Right. So next thing is write an equation for the reaction between hexa aqua cobalt 2 plus ion and NaOH. So as we have already discussed, that an acid base reaction would occur. So cobalt hexa aqua cobalt 2 plus ion will react with hydroxide ions, with 2 moles of hydroxide ions. And now you can write the formula in 2 different ways. Either you can just simply write it in this way, or you can just write it in the form of complex, which is COH2O4. Basically what happens here is that the cobalt, which is attached to 6 water molecules, 2 of the water molecules loses their protons when OH ions are added, right? So when OH ions are added, 2 of the 6 water molecules would lose proton and convert into OH minus. So we can write the formula in this way as well, COH2O4. Now we are left with 4 water molecules, OH2, and this is same structure or same compound, and this formula and this formula, they both represent the same compound. So you can write it in either way. So let's suppose if we write it like this, COOH2 cobalt 2 hydroxide plus, if you write the formula in this form, then we'll show the loss of 6 water molecules. So this would be 6H2O. Or if you write the formula in this way, then you'll only write 2H2O, because the H ions which would be lost from these 2 water molecules, these 2 H ions will combine with OH ions to form 2 water molecules, right? So on the product side, you'll write this formula plus 2H2O. So you can write the equation in either way. Now, write an equation for the reaction between hexa aqua cobalt 2 plus ion and an excess of concentrated hydrochloric acid. So this is ligand substitution reaction. So COH2O6 2 plus will react with 4Cl minus to give COCl4 2 minus plus 6H2O. So this is ligand substitution reaction. Okay, so the next part is define stability constant. So the stability constant is the constant, equilibrium constant for the formation of a complex from its constituent ions, from its constituent ions, right? So it is the equilibrium constant for the formation of a complex ion from its constituent ions. So write an expression for the stability constant of hexaamine cobalt 2 plus complex ion. Right, so it would be the stability constant for the formation of CO, for the formation of CONH36 2 plus from its constituent ions, and its constituent ions are, it would be formed from COH2O6, cobalt ions dissolved in water, and concentration of ammonia power 6, right? So this would be the K-stab expression for the formation of this particular complex. Give the units of the stability constant of the hexaamine cobalt 2 plus complex ion. So the unit would be the concentration, the unit of concentration is mole per dm cube. This is mole per dm cube as well, and this is mole per dm cube power 6. So mole per dm cube cancels out. So now we are left with 1 upon mole per dm cube power 6. So the unit would be mole minus 6 dm 18, right? And the numerical value, first let's erase it. Now, it is saying that the numerical value of the stability constant, the numerical value of the stability constant of this complex ion is 7.7 into 10 power minus 4, 10 power 4. In an aqueous solution of the concentration of, in an aqueous solution, the concentration of this complex ion is this moles per dm cube, and the concentration of ammonia is 0.480 mole per dm cube at equilibrium. Calculate the concentration of hexa aqua cobalt 2 plus ion in the solution, right? So the value of K stab is 7.7 into 10 power 4 is equals to concentration of the complex is 0.0740 divided by the concentration of hexa aqua cobalt 2 ion. This we have to find out, so it would be X into concentration of ammonia, which is 0.480 power 6, right? So this would be equal to 0.480 power 6, that is equals to 0.0122 multiplied by 7.7. So that is equals to 0.094 0.0942 into 10 power 4 into X is equals to 0.0740. So the final answer would be 0.0740 divided by 0.0942, which would be equal to 0.786 into 10 raised to power 0.786 into 10 raised to power minus 4, or 7.86 into 10 raised to power minus 5, right? So this is the concentration of hexa aqua cobalt 2 plus ion. All right, so this next question, question number 7, is related to organic chemistry. And it says that the structural and displayed formula of three aromatic compounds A, B, and C are shown in figure 7.1. Right, so this is a structure A, B, and C. Compare the relative acidities of A, B, and C. So if we look at structure A, it contains this carboxylic acid, B is phenol, and C is carboxylic acid in which a halogen is also present. Right, so the presence of halogen makes the carboxylic acid more acidic. So that means C would be the most acidic compound. And then A, which is a carboxylic acid, and B is phenol, which is less acidic than carboxylic acid. So this is the order of acidity. C is most acidic and B is least acidic. Now in the next part they're asking explain your answer. Explain your answer. So we can explain it in two different ways. One of which is how easily this OH bond will break to release the proton. And in case of structure C, it would break more easily due to the presence of Cl. As Cl is more electronegative, it attracts the electron density towards itself, due to which this OH bond weakens, right? And the other way is to explain the acidic nature in terms of the stability of the negative ion. Stability of negative ion. So we say that the negative ion which we get from structure C, once it loses proton, would be most stable. And the reason again is because Cl is more electronegative, it attracts the electron density towards itself, due to which negative charge intensity on oxygen decreases, and it would become difficult for it to regain proton. So we can explain it in this way, that as in C is most acidic, C is most acidic due to the electronegative nature of Cl. It attracts the electron density towards it, and OH bond weakens. Right, so this is why it is more acidic. And in case of carboxylic acid, this oxygen is also electronegative. It attracts the electron density towards itself, due to which again OH bond weakens easily. So in comparison to B, A is more acidic due to the presence of the oxygen present. This oxygen, right? This oxygen, it attracts the electron density, due to which this bond weakens. So we can just simply say that in structure A, the oxygen of C double bond O is also electronegative, due to which OH bond weakens, because the oxygen of the carbonyl group attracts the electron density and OH bond breaks easily as compared to structure B. Now, the next part is methyl benzene can be made from benzene by an electrophilic substitution reaction. Methyl benzene. Identify a compound that reacts with benzene to form methyl benzene. Identify the catalyst used. So the compound which we use to form methyl benzene from benzene, that would be alkyl benzene. So we would use, alkyl halide. So that would be chloromethane or methyl chloride, we can say. So it would be chloromethane will react with benzene in the presence of aluminum chloride. Aluminum chloride will act as catalyst in this reaction. The first step in the reaction is the generation of CH3 plus electrophile. Write an equation for the reaction that generates this electrophile. So the CH3Cl will react with AlCl3, and we get AlCl4 minus plus CH3 plus. All right, next part is describe the mechanism for the reaction between benzene and methyl electrophile. Include all relevant curly arrows and charges, right? So now we have to write the mechanism. So this methyl group, it would be attacked by the uh, So this methyl group, it would be attacked by the delocalized pi electrons. These delocalized pi electrons will attract the CH3 group towards itself, due to which delocalization breaks, and one of the carbon atom will be connected to the CH3, and it has an H group attached to it as well, and the delocalization breaks, and now it is only extended to the 4 carbon atoms, right? So delocalization breaks and we get this positively charged intermediate. Finally, this CH bond breaks and these 2 electrons will move back into the ring, and it occurs due to the presence of AlCl4 minus, which attracts the hydrogen towards itself. So we get benzene attached to CH3, methyl benzene, plus H will be combined with the Cl, so we get HCl plus AlCl3, we gains back. Identify a suitable reagent to oxidize. Identify a suitable reagent to oxidize methyl benzene to benzoic acid, right? Write an equation for this reaction using atomic oxygen to represent one atom of oxygen from the oxidizing agent. So we know this thing that alkyl benzenes can be oxidized into carboxylic acids. So the oxidizing agent which we use is hot alkaline KMnO4, potassium manganate. And the equation would be in molecular form if we write the equation. So methyl benzene is C6H5CH3. It reacts with atomic oxygen, right? And the methyl benzene will convert into carboxylic acid. So we get C6H5COOH plus H2O. Right, so 3 oxygens have been added. So we can, to balance this reaction, we'll write 3. So this is the equation for the oxidation of methyl benzene. Next part is methyl benzene and benzoic acid are both nitrated with a mixture of concentrated nitric acid and sulfuric acid to give mononitrated products. The structural formula of these products are this and this respectively. Draw the structure of these 2 products when methyl benzene is nitrated and when benzoic acid is nitrated. So methyl benzene, this is methyl benzene. So methyl benzene is 2,4 director. So when it is nitrated, the nitro group would be either attached to carbon number 2 or carbon number 4. So the product we get is CH3NO2, or you can connect it to carbon number 4. And the other compound was benzoic acid. So this is benzoic acid, COOH, which is 3 director. So the compound which we get from benzoic acid is COOH, 3 nitrobenzoic acid, COOH, and the nitro group would be connected to carbon number 3. So 3 nitrobenzoic acid. The reason is methyl benzene is 2,4 director and benzoic acid is 3 director. All right, now the next part is a reaction scheme is shown in figure 7.2. Describe the reagents and conditions to produce this diazonium salt from amine in reaction 2. So in reaction 2, we have this amine which is converted into diazonium salt. So we know this thing that diazonium salt, the reagent which we need to prepare diazonium salt, which will react with the amines, is nitrous acid HNO2, and diazonium salts, they form at very low temperature because they are highly unstable. So condition would be low temperature around 0 to 10 degrees centigrade. ठीक है जी. Describe how this CH3C6H4OH can be produced from diazonium salt in reaction 3. So this is phenol. right? This is we get phenol when this diazonium salt is decomposed at high temperature, when temperature rises above 10 degrees centigrade. So at temperature greater than 10 degrees centigrade, the diazonium salt will decompose in the presence of water, H2O, right? So when we add water and raise the temperature above 10 degrees centigrade, this diazonium salt will break. Now the last part of the question is draw the structure of the di molecule Y formed when this diazonium salt and this phenol react together in reaction 4. Describe the condition for this reaction. So to draw the structure, you can just simply look at these two compounds. This is diazonium salt, this is phenol. So a condensation reaction would occur, right? A condensation reaction would occur. The benzene ring from the phenol will lose. The benzene ring from phenol will lose this one hydrogen atom, right? And diazonium salt will be connected to the benzene ring. So the structure which we get is CH3, C6H4, N double bond N, which would be connected to C6H3. Now three hydrogens are left because one would be lost when the nitrogen would be connected to the ring. CH3OH. So this would be the structure of the dye which we get when both these compounds will react with each other. And the condition would be NaOH. This reaction occurs in the presence of an alkali at temperature between 0 to 10 degree centigrade. Alright, so this is the end of this question. Alright, so let's start with question number 8, which says that when answering this question, it should be assumed that together all the hydrogen atoms in a benzene ring result in a single unsplit peak at 7.2 in a proton NMR spectrum. So the hydrogen atoms of benzene ring will give a peak at 7.2, which would be a single unsplit peak. The structure of 5 isomeric ketones are given, and they have given them names P, Q, R, S, and T. Identify all the chiral carbon atoms on the structure above. Label each chiral carbon atom with an asterisk. Alright, so the chiral carbon atom is the carbon which is connected to 4 different groups, and there is only one chiral carbon atom which is present in structure T, and which is this carbon. Now this carbon is connected to 4 different groups: a hydrogen, a C6H5, COCH3, and CH3. So it is connected to 4 different groups, and there is no other chiral carbon atom. So this chiral carbon atom is this carbon is chiral carbon. Now, the next part is the proton NMR spectrum of one of the 5 isomers P, Q, R, S, or T is shown in figure 8.1. So this is a proton spectrum of any one of these compounds. Identify which of the compounds give this spectrum. Draw the displayed formula of the compound you have identified, and identify the protons responsible for the peak at 3.7, 2.5, 1. The structure you have drawn, right? So now this is the proton NMR, right? And it gives 4 peaks. That means we have 4 different environments in our structure, first thing. And this 7 at the peak at 7.2, this is obviously from the protons in benzene ring. All right, and then we have a triplet at ppm 1 and a triplet at around a quartet at 2.45 and a singlet at around 3.6 or 3.7. It is a singlet, right? So we have 4 different environments in our structure. So if we look at the structure R, so this has these protons will give the peak at pH at 7.1, right? And these protons, these are 3 hydrogens which are connected to this carbon which has 2 hydrogen. So 2 plus 1, these hydrogens will give. First of all, let's count the number of peaks this will give. So 1, 2, 3, and 4. So there are 4 different peaks right? So we get four different peaks. One, the C6H5 will give a peak at 7.2 because these are hydrogens of benzene ring. Then these two hydrogens, they would give a singlet because they are only connected to they are connected to this carbonyl, which has zero hydrogens attached to it, so this would give a singlet. And this carbon which has two hydrogens attached to it, so this would give a quartet because the next carbon to it has three hydrogens, right? So this will give a quartet and this will give a triplet. So we have four different environments, and now the structure is R. We have to draw the displayed formula. So this is C6H5, C6H5, then CH2, CH2, C double bond O, CH2, CH3. So this will give a triplet. Splitting pattern is due to the protons on the next carbon atom. So this will give a triplet because the next carbon atom has two hydrogens on it. So the formula for the splitting pattern is n plus 1. So the splitting pattern of CH3 is 3, a triplet. Then CH2 will give a quartet because the carbon next to it has three hydrogen atoms. So this will give a quartet. And these two hydrogens, they are connected on this side with carbonyl, which has zero hydrogens. And on the right side, they are connected to this carbon, which is again has no hydrogen atom, right? So this will give a singlet. So name the splitting pattern of the peak at 3.7. So the peak at 3.7, this singlet, this is due to the CH2 group. Right? This CH2 group is responsible for the peak at 3.7. These CH2, they are responsible for the quartet at 2.5. And this CH3, this is responsible for the triplet at 1.0. Name the splitting pattern of the peak at 3.7. Explain why it has this splitting pattern. So the peak at 3.7 has a splitting pattern of singlet because the carbon next to it has zero hydrogens. Right. Now, the next part is choose from the letters P, Q, R, S, and T to identify the two compounds that each have a doublet peak in the proton NMR spectrum. Two compounds with a doublet. So if we look at the structures of these compounds, the two compounds with a doublet. So structure P, this would give a doublet. These CH3, they would give a doublet because these CH3, they are connected to CH. So CH means it has single hydrogen. So their splitting pattern would be 1 plus 1. That would be equal to 2. So P will give a doublet and Q, T. Alright, so T would also give a doublet because this CH3 is connected to CH, which has one hydrogen. So the splitting pattern of this CH3 would be doublet. 1 plus 1, this would give a doublet as well. So P and T will give a doublet. The compound with only 3 peaks in its proton NMR spectrum. The compound with 3 peaks. So let's count the peaks by each of these compounds. So 1, 2, 3. So P would give 3 peaks. So P is the compound which will give 3 peaks. And this is P. Suggest a suitable solvent that should be used for obtaining the spectrum shown in figure 8.1. So the suitable solvent, it could be CdCl3 or CCl4, carbon tetrachloride. The proton NMR spectrum of compound T is compared in the presence of D2O and in the absence of D2O. Describe any difference between the two spectra. Explain your answers. So D2O is basically used to remove the protons of NH2 or uh, OH, but because structure R has no OH group or NH2 group, that means there will be no difference in the presence or in the absence of D2O. So there will be no difference as no proton exchange occurs. All right. Now, next part is complete table 8.1 below to give the number of peaks in C13 NMR spectra of each compound. So we have to count the number of peaks. So the number of peaks would be 1, 2, carbon 13 environment, right? 3, then these two are same, 4, these two are similar, 5, and this one is different, 6. So this compound will give 6 different peaks. Now if we look at this structure, this has this plane of symmetry. So these two carbons are similar, 1, 2, 3, 4, and 5. So 5 different peaks. Then in this structure, this is a plane of symmetry. So 1, 2, 3, and 4. So 4 different peaks. And in last structure, this is the plane of symmetry. So 1, 2, and these 4 are all same. So they would give the same peak. So 3 peaks, right? So this is the end of question number 8. And now let's move on to the last question of this paper. Tyrosine and lysine shown in figure 9.1 are naturally occurring amino acids found in protein. So this is the structure of tyrosine and this is the structure of lysine. The isoelectric point of lysine is 9.47. Isoelectric point is when it exists in zwitterine formation. Draw the structure of lysine at the stated pH in the boxes below. So lysine at pH 7, that means below isoelectric point. So at pH below isoelectric point, that means it would be the acidic range. So in acidic range, there will be H plus ion present. So this will gain H plus, it will remain in COOH form. NH2 will become NH3 plus, and this NH2 will also become NH3 plus. All right, so the structure would be COOH, NH3 plus, 1, 2, 3, 4, 5, NH3 plus. Or if you draw the structure in this way that you only show up one positive charge, so this would also be considered as a correct structure, because at pH 7 we can say that lysine either it gains 1 proton or 2 protons. So both these structures would be correct. Lysine at pH 9.47 would be in zwitterine formation. So in zwitterine formation, this would be COO negative, NH3 plus, and rest of the structure would be same NH2. NH2, or if you draw a negative ion here and a positive ion here, this would also be considered correct. Then this would be NH2, right? So both the structures are correct. Now at the pH 12, that means in basic medium, we get COO negative, NH2, 2, 3, 4, NH2. So this would be the structure of lysine at pH 12. So just remember this thing: in acidic range, the amino acids, they exist in positive ion formation, and in basic range, they exist in negative ion formation, right? Now the next part is, when ethanoic acid is treated with PCl5, product D is formed. When D is added, ethanoic acid is treated with PCl5, that product D would form, that is acyl halide. So it would be CH3, C double bond O, Cl. When D is added to tyrosine, two different isomeric products E and F are formed. When D is added to tyrosine, which is CH3, C double bond O, Cl. So they are saying two different products are formed. E and two isomeric products are formed. E has an ester linkage, F does not. Draw the structure of D, E, and F in the boxes below. right? So we have already drawn the structure of D, which is ethanoyl chloride, CH3, double bond O, Cl. This is structure D. Then E is an ester, right? So this would be an ester. So we can say that acyl halide will lose this Cl, and from phenol this OH group, this H would be lost, right? So this H would be lost. So we get this phenyl ester. So CH3CO, CH3, double bond O, and then we have this benzene ring, and rest of the structure is similar, right? So same structure. Then F is not an ester, right? F is not an ester. So this would be an amide, because acyl halide can also react with NH2, right? This Cl would be lost and H would be lost. So again, HCl would be lost, and on this side, this we are only left with a hydrogen, and it would be connected to C double bond O, CH3. So these two structures would form. So I hope this is clear to all of you, right? So these three structures would form. Now, complete table 9.1 by drawing the structure of the organic product formed when tyrosine reacts with each named reagent. Ignore the directive effect of this substituent, right? So an excess of bromine, when we add an excess of bromine, bromine will react with the ring, and let's just erase this one first. So when we add bromine, bromine will be added to the ring at position number 2, and position number 4 is already occupied, so position number 6. So this would be the structure when bromine is added, right? And then an excess of NaOH aqueous. So NaOH is a base. It will react with both phenol and carboxylic acid. So this would be deprotonated, and this would be deprotonated as well, right? So this would be the structure when you can just simply remove this bromine from here. So this would be the structure when it reacts with sodium hydroxide. And last is an excess of nitric acid, aqueous nitric acid, right? So nitric acid, again electrophilic substitution would occur, and this time we get NO2 group at position number 2 and position number 6. So these would be the three structures. And now the next part is a mixture of tyrosine and lysine can be separated by thin layer chromatography. Under certain conditions, the RF value of lysine is 0.14 and the RF value of tyrosine is 0.45. Explain what is meant by the RF value. So RF value is the distance traveled by the substance. Distance traveled by substance divided by the distance traveled by solvent. So just an explanation for the difference in RF values. So the RF value of lysine is 0.14 and tyrosine is 0.45. So we can say that tyrosine is more soluble in mobile phase and lysine is more soluble in the stationary phase. So tyrosine is traveling more. That means tyrosine is more soluble in mobile phase and lysine is more soluble in stationary phase.